I like going to these hacker camps, and so I've done some talks here before about the electromagnetic field, which happens in the UK every couple of years. And so here's me at Chaos Communications Camp, which is one of the big ones in Germany. And that's me doing my volunteer shift in the bar, in the no photos allowed area, having my photo taken, serving some beer. So this camp is, I live in Berlin. So on this top map, is where I live at the bottom. And I rode on my bike 70 kilometers out into the countryside to Chaos Communications Camp. And then the second map is the site. So that was 1 day worth of my GPS movements around the campsite. So that's just to give you a bit of sort of physical context for where I'm coming from for this. And this kind of camp, it's pretty common to make badges. And I don't mean badges like a badge with your name. I mean a badge that is basically a small computer. This is the collection I have in Berlin. I have some more in England from other camps. So these are mostly Wi-Fi enabled Python devices that consist of something that could run some version of Python, and word sensors, displays, like cool stuff. And usually with your camp registration fee, you get one of these badges. That cap at the bottom was a badge that was a learn to do SMD surface mount, whatever, surface mount soldering. Anyway, that was a project for that. So there's a lot of surface mount stuff on the back of that. The one on the left is from EMF Camp 2022. The one in the middle is from Chaos Communications Camp, and the one on the right is from a camp I didn't go to. And it's got a RP2040 CPU on the back. So that's my badge collection at the moment. Also, in German culture, I've never really seen it anywhere else. There's this culture of just you stick it, if you've got stuff you don't want, but you think someone might want it, even though it's probably crap. You stick it outside your house and you like zu verschenken, like to give away. So what English people would say, I'm going to take this to the charity shop. Germans tend to just stick a box outside their front door with, please take my crap. And that was some of these boxes at Chaos Communications Camp. And in one of those boxes, actually this badge on the left, the Born Hack 2022 badge came from one of those. But right next to it, in a box, was a few of these. And it's labeled up as Born Hack 2021 conference badge, but it clearly doesn't look like any of the badges that I just showed. It's just a circuit board with some labels on it. And I thought I'd take one and do something with it. So this was in August, but I've only just got around to doing something with it. And the story behind why this badge doesn't look like those other Python peripheral style badges is because in 2021, there was a massive shortage of stuff. So anything that involved electronics around 2021 had supply chain problems. And I think maybe the Raspberry Pi 02 wasn't available for a very long time, basically because of this same supply chain shortage. So the people organizing Born Hack Camp that year decided that they're not going to be able to make a credible badge in the traditional style that year. So they were going to go for something they could make, which was a build-it-yourself circuit board. So they made this. It's basically a prototyping area on the outside, the left or the right, depending on which one you're looking at. It's got a few circuit traces. So it's got some traces for VCC, which means the supply voltage. Ground is ground, and then I2C, that's the SCL SDA, is the I2C bus and some general purpose input output pins, and it just connects them from a few different places. So there's a place for you to solder on what's called a shitty add-on connector, which is the 6-pin thing in the middle. There's a quick or stemmer connector, which is pretty standard if you've been using anything from, I guess, Adafruit and SparkFun, maybe someone like that. Anyway, but they're just connections. When I say this is an I2C bus, it doesn't actually go anywhere. When I say it's ground, it also doesn't go anywhere other than the labeled connections. It's not going into any chips or components because those components don't exist. So I'm like, all right, I'll take one of these. Seems kind of cool. I have this habit of buying blank notebooks because I think they're cool. And this was kind of like, oh yeah, some blank thing. Maybe I'll come up with some use for it later. So then I'm like, what can I build on this thing? Well, let's try and avoid a microcontroller. Maybe I could avoid any kind of chip at all and just use discrete components. I like making interactive stuff. If you've seen any of my other stuff before, I like LEDs for sure. I have to build the circuit, has to fit on the board. That's an obvious constraint. And I would like to build a circuit that I can mostly understand. So I had some transistors in a bag and I've been playing with them a bit. And I thought maybe I can build something. So here's a picture of a transistor from my local parts supplier. They cost 7 cents, so around 7 pence each. So they're not particularly expensive components. They're also not particularly complicated components. And so I had a search on Google, and I'm like, what kind of circuits can I build that are gonna fit this fit these constraints? The two that I ended up on my shortlist are an SR latch, which is a 1-bit memory. That's what I'm going to talk about. And the other one I thought about building would be an XOR logic gate. That seemed about the right size as well, but I didn't pursue that. I chose the first option, which is an SR latch, which I'll talk about now. So what I've ended up building is a 1-bit memory on this board. So what I mean by that is it's memory. It's like disk or RAM. It's going to store some information. And it's 1 bit, so it's going to store 1 bit of information. So that's the same as you say, I've bought a 500 terabyte hard drive or build a 500 terabyte storage system, where you might say that, or a floppy disk contains 1 megabyte. Here, we're just going to store 1 bit. And what's a bit? Well, bit is just a very simple unit of information. It's a yes/no question, perhaps, or it's true or false. Or if you're doing numbers, then it's a number 0 or 1. One of the original cases, way before computers, was the Jacquard weaving loom. Are we going to weave this particular, I guess, waft thread over or under one of the cross threads? And that's a use of bits from the 1800s. So I was at the German Technical Museum the other day, and there was some really nice physical bits manifest on paper. You can either have a hole or not have a hole, a choice of 2 things. And again, some 5-bit paper tape with every place you can either have a hole or not have a hole. So each of those little dots or absence of a dot is 1 bit of information. And if you stick bits together, you end up 2 bits lets you have 4 choices. 8 bits gives you 256 choices, and we call that a byte. 50,000 bits, you can have a page of text. 32 million bits is enough for a JPEG. The JPEG of the punch card I just showed, for example, is 32 million bits. So this really simple unit of information, stick it all together, you can store a lot of stuff. And here's a picture from the Jacquard loom. I'm not sure when this was actually woven, but the technology is from the 1800s. So every time when this is woven, the thread goes over or under another thread, that is one bit of information coming off some punch cards. So that's all complicated. This is what I built. There's my personal instance of this board with the components I put on it. And it's going to store one bit of information. So there's two LEDs, there's two buttons, and when you power it up, it will have one LED on. And if you want the other LED on, you push the button. So you push the button on the left, and the red LED will light up. The left LED will light up. And if you want the right LED to light up, you push the right-hand button, and it will remember the last button you pushed. So that's the memory bit of it. And the fact that it's one bit is the fact that there's a choice, either the left or the right is illuminated at any one time. Here's my awful soldering. I'm terrible at soldering. This is what the back of the badge looks like with this Vera wire pen. I almost omitted this slide because it looks so horrible, but I put it in for completeness anyway. So what's a transistor? The component I wanted to use is a transistor, and this is semiconductor. According to Wikipedia, it's a semiconductor device used to amplify or switch electrical signals and power. And there's a lot of different kinds of transistors. They all behave a little bit differently, but they're all fundamentally this kind of switchy, amplifying kind of device. If you've done anything with relays, like these little physical switches that are powered by magnets, or if you're from the 1930s, you might have seen valves or tubes. They're broadly similar devices to that in behavior. So if you were in, say, 1960, the kind of transistor I'm using is the kind of transistor that you might build a computer out of in 1960. So maybe 2000 transistors for all the logic. More modern chips, I think that Wikipedia page transistor count that I pasted at the bottom, they say someone's built a memory device with 5 trillion transistors. So they're absolutely not packaged in the way that they're packaged on this board. They're much smaller and all on one chip. So this is the circuit diagram for what I built. So that messy board that I showed a few slides ago, this is the schematic that I built in a tool called KiCad, which is a board designer. So I'll go through how this works. I'm going to hide some stuff first. So this is the core one bit memory. Got 2 transistors. That's this circles on the left and the right, and a few resistors. And so what I'm going to do is talk through some of the flows of electricity and current on this diagram. There we go. So if we imagine this transistor on the left is off, then we can pick a path for electricity to flow and think about what's going to happen as it flows along this pink channel. Well, it's going to flow from up at the top, which is +3 volts, down to ground at the bottom. And it's going to flow through these 2 resistors and then through what's called the base of the transistor. This is like the switching input. And what's going to happen is if we put a lot of current into this transistor, it's going to turn on. And if we don't put much current in, it will be off. So transistor, it's quite like a diode. If you put electricity through it, it's just going to drop a certain voltage. It's going to drop about 0.6 volts. So the rest of the path is going to have to drop from our 3.3 volt power supply about 2.7 volts. And with all these two resistors, we're going to get about 200 microamps flowing through that path, which is a very small amount of electricity, but it's enough for the transistor to turn on to become saturated, they call it. And what that means is it will allow electricity to flow from what's called the collector, this little bit on top. So there's another current path, the green path here, and electricity will flow through here. It will let lots of electricity through the transistor, which means this point in the middle that's labeled 0 volts, the voltage there will be 0 volts. And that means we're not going to get any current flowing through to the left-hand side transistor. So that transistor will be off. And that means on the left-hand side, the corresponding point will be about 2 volts again, and current will flow like this and keep the one on the right on. So they're in a feedback relationship. If one is off, it causes the other to be on, and if one is on, it causes the other to be off. And this is a symmetric circuit, so I've shown it one way around, but it could equally well be the other way around. And when you first power it up, it'll just go into an arbitrary state based on things like the particular property, the particular manufacturing quality, for example, of the transistors and how bad the soldering is and things like that. So we've got this symmetric circuit, and that's the two states that is binary. We need to have two different states, and the states are the one on the left is on, the one on the right is off, or the other way around, the one on the left is off and the one on the right is on. But what I've shown so far is how they maintain one particular state. And what we want to be able to do is push some buttons and have it flip into the other state. So if I uncover here, if I uncover the buttons, they were here under those blue squiggles. What happens is if you push one of the buttons, if you push this button on the right, it'll short circuit the current so that it doesn't flow through that transistor on the right anymore. And then the right transistor will go off, which means the left transistor will go on, which means it will continue to persuade the right transistor to be off. So even when you let go of the button, it will now stay in this new configuration the other way around. And then on the left-hand side, we've got the same button over here that will let you flip back the other way. And then the other bit of the circuit, which was hidden under this, is the LED driver circuit. So there's a point here where just above the transistor that's off, we draw current off through a 12 kilo ohm resistor into a transistor, and that's enough to make that transistor turn on. Well, we do the same. We draw current off through a different 12 kilo ohm resistor into another transistor at the far left. But this time, instead of using it for this sort of logic control, we're using it for current control, so power switching. So the sort of currents we want flowing in the logic, the center area of this circuit is sort of a few hundred milliamps, really small. But I wanted to drive some LEDs, and LEDs need a lot more. They need about 20 milliamps worth of electricity and worth of current. And so what's happening on the left of this diagram is when this transistor is activated, which will be exactly the same as when the right-hand transistor is activated, it's going to let a bunch of current through that will then let this LED illuminate itself on the left. And we've got the same setup on the right, symmetrically. So we've got two uses of transistors here. One is a sort of logic, using the smallest amount of currents we can, basically, to make other transistors react in interesting, complicated ways. That's the sensitive transistors. Then on the outside, we've got these LED driver transistors, and all that wants to say is, you give me a little bit of current, and I will let a lot of current through for the thing that I'm controlling. And then I added in, on this point, I added in another resistor and a transistor, just like I'd already done across the middle. So you might ask, can I just keep adding in more resistor transistors and driving other things, driving more LEDs, driving other circuits? And the answer is sort of. So this point that I've put a big circle around is a kind of input-output point for being able, that this is the place where you would attach new stuff. And so I could have attached an external LED. Here's the circuit. That green circle point there is the tip of the this resistor that I put this green crocodile clip on in real life. And what I've done is I've wired it into a BBC microbit. The BBC microbit is the input from the BBC microbit behaves just pretty much just like that, like those two transistors. So it will either be activated or not activated. So I can play a video. Won't do a live demo, but we get a smiley on the BBC microbit, and as I change the state of the 1-bit memory, the BBC microbit is able to detect that its input is changing. So that's just a normal GPIO, same as the GPIO pin on the Raspberry Pi. And similarly, the BBC microbit is able to do the same as pushing switches. So those little buttons that are on the board that can change the level, change the voltage level at that point to turn the transistors on or off. The BBC microbit can do that through, it turns out, exactly the same cable. And so the BBC microbit is going to count down, and then it's going to change the state. So for 3, 2, 1, 0. Boop. Okay, so that's the BBC microbit is able to basically do the same as pushing the buttons by changing voltage levels there. Okay, so that's what I built. Here's some links for various things. You can download this, or you can download the designs for this badge, not the circuit I built, but the badge that I picked out the box. You can get the plans for that on GitHub and print them yourself. There's a talk all about the badge, a little bit about the background with parts shortages and stuff is available there as well. There's the Wikipedia page that I linked to before. I just today saw a pretty interesting documentary from Hackaday about badges at DEF CON, I think, in the US, and a couple of image credits. Okay, so that's my talk.
We have some questions. So are you planning on extending that, or are you gonna keep playing, or what's your plan with it?
I'm just gonna wear it now. So the one thing it doesn't have, which is the last slide that I skipped because I never got around to writing it, is it doesn't have any power supply. And sort of one of the things to properly be a badge is it needs to be able to power itself rather than you having to plug yourself into the mains or whatever.
Yeah.
So I've got a live poly battery and a connector, and I'll probably solder that on. But other than that, I think it's
So
a done.
the badges you get for those various events and stuff like that, how long do the batteries last? Sounds scary.
In many hours. Like I mean, the power is going into the screen backlight, right? It's the same as your phone.
Yeah.
So if you're powering the screen the whole time, then no, it's not going to last that long. But
Yeah, I was wondering if anyone has any experience with the Pico W, because it seemed to eat my batteries fairly quickly. The powering a screen as well, I guess that's the biggest cost, isn't it? Biggest.
And
right, go
so
on.
a lovely little introduction to transistors. I used to play around with them many years ago. The thing that always used to puzzle me was what were the correct values for the resistors you use.
Yeah. So
How much of this is trial and error, and how
I would
much?
say culturally, you get this a lot in ham radio, and I've seen it a lot in online electronics, specifically electronics forums of like patronizing dicks who are really unwilling to explain stuff, and they will always pop up with when you post a circuit and say this is wrong, you should have used this kind of resistor, and then they will say there's no reason for it, but you should have used this. And it's like, mate, that's not helpful at all. But as far as I can tell, it doesn't matter too much. All right, so let me do my slides again.
Yeah, I think you can often be out by a factor of 10 and it'll still work.
Yeah. Hold on. So
Yeah.
I'm just trying to do a screen share again.
Yeah, it's really an analog circuit
Slides?
to calculate.
Where have you gone? Where have you gone? Here. No, here. No, here. All right.
So I was surprised how much voltage you see you lost in that. It's 0.6 volts, it's quite a bit.
Yeah, let me come to the diagram. Here. All right. So basically, can you see my mouse cursor?
Yes.
Okay, good. So this thing will basically, for every electron that comes through here, so every unit of current, it will let between, for this particular transistor, it will let between 100 and 800 electrons through here. So if you feed 100 microamps in here, it's going to let a lot through. And at some point, it hits this limit that's called saturated, which means you put loads of current in here, it's just going to let its maximum amount come through. So you've got all these formulas about, you can calculate the amplification and all of this. And then you're just like, well, forget all that. As long as you put enough through, it's going to let the maximum through. So beyond a few hundred microamps, putting more current through isn't going to change anything, right? So this resistor here is controlling how much current goes through. And yeah, if I halved that and made it 6K, nothing would change in this circuit. It would just get a little bit warmer, I think. It would waste more electricity, maybe. But the transistor would still be letting its maximum amount of current through. What would happen if you went down, made the resistor too big, is there wouldn't be enough current flowing through. And then that would limit what was happening here. But you can go over the top, and the bad side is that it gets warm, I think, not that it doesn't switch properly.
Okay, Ben, thanks for that.
Got one quick question.
Mm.
That would be about your 500 terabyte hard drive. How did you, or excuse me, storage? How did you do that?
I don't have a 500 I don't have a personal 500 terabyte storage system, but I do work on high performance computer systems with petabyte scale systems, storage systems. But those are like professionally administered racks full of.
Well, you didn't you say you had made a 500 terabyte storage?
No.
Oh, sorry.
No. I do work with them, but I haven't made one.
Okay.
Yeah.
It would take an awful lot of transistors.
Oh yeah.
No, I don't mean make it from scratch. I mean, how did you put it together? It's a 500 terabyte drive by itself is very expensive, but I wondered if you had somehow or other put together a cluster or something like that.
Yeah, the stuff that I work with is basically clustered storage. So lots of essentially the biggest off-the-shelf hard drives that you can buy times a lot, plugged into as many computers as you need to drive them, which is kind of fun, but also the performance can sometimes, you get a lot of storage space, but the performance just turns to crap, because there's a lot of coordination overhead to make it all work together. So it sounds cool on paper, it's like, yeah, cool. But there's downsides as well.
Well, any other questions?
Just one comment. I think for obvious reasons that circuit is called a bistable.
Yeah, bistable. One of the weird electronics forums things I've encountered is people arguing and telling each other they're definitely wrong about, is this a latch? Is this a register? Is this a bistable? Should a bistable make itself change states automatically? So I tried to avoid all of that terminology.
I see that the AI calls it a bicycle.
Bicycle? Where is the AI?
I've got the comments on, yes.
Yeah, there's the AI agent, whatever they call it, or to Zoom. You want to take a look at that? Cool, thanks very much, Ben.
Yeah.
So let me just share my screen. Just give me a sec.
Hello? Hello, can you hear me?
Yeah.
Yeah, this is elementary stuff really about I'm always I have to think and double think about polarities, voltage polarities, supply, of errors in components like diodes and transistors, and whether it's conventional current or actual electron flow. Could you please run through those for us?
Okay.
For me anyway.
Yeah, hold on. So the top of my diagram, I'll just do a share again. Hold on. One more share. You'll have to wait a moment, Richard. Yeah. Can you see the circuit diagram? Yeah. Okay. So this line all across the top is positive voltage. So plus 3.3 volts in my situation. And this line on the bottom is 0 volts, so ground. So now I have to think about which way electrons would actually flow. Electrons flow towards negative charge. So electrons flow downwards on this diagram.
No,
Wait, is that the right way? No, electrons flow upwards on this.
other way
diagram.
around. You see,
Yeah.
you see my confusion.
No, no,
I think the
no,
electrons
no, it's
from ground up towards the positive voltage.
whatever. Yeah, yeah. Yeah, the charge is going upwards.
It's
But
It's-
but I definitely tried. I thought about there's a section I could have put in, which is what's happening inside the transistor. And I always get confused, basically the same confusion you have about what's happening inside there.
yeah. As I understand it, the arrows in both the diode and the transistor are the direction of flow of holes. In other words, anti-electrons.
Yeah,
So, you know, whoever defined conventional current, which is the opposite of electron flow, has a lot to answer for.
yeah.
Is that right then? The arrows are opposite to the direction of electron flow generally.
That's right. Yes.
Yeah, the electrons are going upwards, right? Yeah.
Yeah, those are NPN transistors. If you use PNP, everything would be reversed.
Yeah, but you switch your circuit around a bit for that. Yeah. Yeah, mostly I try to avoid thinking about where the actual electrons are flowing.
Don't normally have to.
Yeah. Cool.
Cool,
All
thanks.
right.
Thanks very much.